Hi, Randy, K7AGE. Welcome to the Ham Shack. I was on Digital Rancher last night with Rob, and we were talking about the TinyGS and the Cornell Alpha satellite project, and I put together a few slides. The show went well, except I couldn't get my good microphone to work for some reason. I don't know what was going on. So I thought, since I had put together kind of a presentation of all this, I thought I would turn this into a video and put it on my channel. You know, the content was sitting on the hard disk, so let's turn it into a video here. Let me switch over here to so this is where we start off here. It was on the Digital Rancher YouTube channel, Rob's channel, last night, and I talk about my satellite station I have built here in Gold Beach, Oregon, on the southern Oregon coast. And then we talk about TinyGS, and which is tiny ground station. So we have a big ground station and a tiny ground station we'll cover. And this leads into the Cornell Alpha satellite project with a solar sail that's coming up next month. So this all kind of sort of started with a tweet here. I sent this out. I posted this on October 23rd. I said, we can help Cornell's Alpha Cubesat mission by setting up a simple satellite receiving station to receive data. This is the same setup as the TinyGS satellites use, but with configuration to only listen to the Alpha satellite. And we'll see why that's going to be important in a minute. And a few nights later, I had zonked out on my sofa here in the Ham Shack man cave, and I saw a video up on my YouTube stream, and it said, something about the Alpha satellite. I thought, oh, I'm interested in that, going down that path. And this is where I connected up with Rob from the Digital Rancher. This is his late shift that he does on Friday nights. It's a live stream. I was watching it later. And I tweeted this. So here I am with my feet on the sofa, watching him talk about how he got interested in pursuing this based on my tweet. So last night I was on his live stream. The week before, he covered the Alpha satellite and the Cornell mission and all that, and kind of went through their extensive, very well written instructions how to acquire all the bits and pieces you need to build the ground station, and how to configure it, and all of that. So that's what he did last week. Last night, he was his plan was to go through and configure the hardware and software to get it all to work. And I said, hey, if you'd like, I could join you and we could talk about this stuff together. So we were on there last night, and we had a good time, a lot of fun. Really unfortunate the audio sucked. So this will help clean up at least my content that was part of last night. So I talked about this, but now I have some photos to show here. I just recently rebuilt my satellite station here in Gold Beach, Oregon, but I did have a Oscar 13 class station when I lived in Grass Valley. We bought this house and moved in July of 1990. We bought it from a ham, but I did not know him, Bob, NA6E, at that time. In fact, when he put the house for sale on the market, he tore his HF tower down, and he says, people come to look at a property and all they do is look up. So, but he did have his satellite station still up. It was on a short tower, and years later, when we put an extension on the house, which became my Grass Valley Ham Shack, I moved the whole array up on top of a 40-foot tower to clear all the local oak trees. So an Oscar 13 station needed big antennas because its orbit was a very elliptical orbit. This isn't 13s, but this is a similar orbit. So I believe in Oscar 13, now I'm looking at 35 years of memory here, was about a 16-hour orbit, which meant during this time out here, the tracking was very slow. It wasn't moving much, but it was far away, like 40,000 kilometers. So to get to it, and Oscar 13 had a linear transponder. So the 2-meter antennas that Bob had, which became mine, were a pair of KOM 22Cs. So these are 11 elements in the H plane and 11 elements in the V plane, phased together for circular polarization. There was actually a relay on there so you could change it between left and right hand. So 11 elements on that antenna, 11 elements on that, so I had a total of 44 elements on 2 meters. It was a big antenna. Each of these were about 19 feet long, physically large. They worked really well. For the 435, I had I think it was called an F9 FT. I think that's what it was, even though I show FT9T here. Now that I speak it, I think it was F9 FT. Anyway, excuse me, it was 38 elements, so it's 19H and 19V. Polarization was fixed on that. So when we put the house up for sale to move up to Go Beach, all this came down and basically went into storage until just a few months ago. The Oscar 13 was a large satellite. This is about, 5 or 6 feet across here. And it had different transponders on there. It had, attitude control in there. I think there was some maybe microwave type of antennas on the top here. This doesn't appear to show the antennas, so it would require some pointing towards the Earth, as best as I can recall from those days. So when I rebuilt my satellite ground station here in Go Beach, I did not want to put up those big antennas. I did not want to put them up in the air where you have to get up on top of a tower. So I used basically only about 6 feet of the 2-meter antenna. So it gave me 6 elements, H, N, and V. And I took the 10-foot long 435 antenna and I just used one section that had the driver on there. And when I put the analyzer on there, everything looked fine as far as SWR. It was going to work. And I just have it mounted on the ground. I have a whole video of me putting my whole Go Beach station together here. But this is just to show you what a larger ground station consists of. I use a ICOM IC 7900 and of course the Yaesu rotator, but the key to make this thing work is the CSN SAT satellite controller. This thing, the little computer in here knows all the orbital elements, so it knows where all the satellites are. It gets its time off the web. It controls the radio, so it puts in the up and down link frequencies, the mode. Here it's on a linear transponder, probably RS440, RS44 at that time, LSB and USB. It sets the frequencies and it controls both the up and down as far as Doppler, so it's constantly changing the frequency during the pass. It also controls the Yaesu rotor box, so now it's pointing the antenna. This box presents a web page, and that's how you control it. So up in this area is all the satellites that I am interested in. You can choose and select what you want to show here. Here it says we're following RS44 at the moment. This is a polar plot, so this is the sky above me, and it shows here that the satellite starts down here at the green, it progresses to the red. The current satellite position here is at the white square, and the antennas here at the orange. And the antennas lead and lag as the satellite moves, but the pattern is wide enough, it doesn't really make any difference. Here's a map showing the ground cover of the satellite. I'm here at this little X. So it's getting low in the horizon, which we can see here. This area down here is a bunch of data, and it shows that the current satellite position is at 7.1 degrees. And I have 4 minutes and 16 seconds till I lose the signal. Maximum elevation on this pass was 8.1. This area here shows all the radio control parameters, so you can load in different presets, let's say. So here it is for the linear transponder. You go up on 2 meters, down on 435, and use sideband. And I've actually tuned across there and heard 5 or 6 different conversations going on at the same time. And RS-444 is kind of nice because it's in a higher orbit, and you can use it for 15 to 20 minutes versus maybe 10. And there's like a preset for FT4 and things. So that's what a large ground station consists of, and there's a lot of moving pieces there, and it all adds up cost-wise. There's many thousands of dollars being run there. Radio, rotors, antennas are the main things. Now we move to TinyGS, so tiny ground station. This is the opposite end of the spectrum here as far as complexity. And if you go to the TinyGS website, you'll see this map page, and you can see all these greens are all the ground stations around the world. Got a lot of them here on the East Coast, a scattering on the West, South America. Europe is heavy into this. Down here in the Middle East, a few in India, the Pacific Rim, Indonesia, Japan, a couple here and there in China. So, and you can see how many the satellites here floating all around, and there's a lot. So there's, at this point, when I grab this image, there's over 1,900 active stations, and over 43,000 data packets have been recovered. Now, there's not a lot that we do as users of the ground stations with this information. The packets get received, and the controller for the TinyGS sends it up to their servers, and the universities or whoever is sponsoring and operating the satellites receive that data. We can see the data, but I think the main thing here is that it's fun to build this low-cost, simple station, as we will see. It's a great test bed to improve your station, because you can try something and let it run for a couple days, try something else, let it run for a couple days, and I have some examples of that here as we move along. So it's a neat educational thing. It's really low cost, and you can really have a lot of fun playing around with it. Here's just 4 examples of the many different satellites that are in orbit. The TinyGS satellites use LoRa, which is the same technology as in our mesh-tastic radios, so it's long range, low power, and it's amazing. It really amazes me how well these things work. So, when I say it's the opposite end of the spectrum of what you need, this is it. This antenna. So this is a ESP-based 32 board. Same thing as we use in the mesh-tastics, although we're on 433 megahertz here, not 915. So you can't take your mesh-tastic board and use it for TinyGS, although there are some 915 satellites, but everything here is 433. So it's a similar board, just when you go to buy them, you can select different frequencies, different bands. So this is the 432. So this has the little computer on board. It's got the radio on board. The computer knows what the orbits are. It has Wi-Fi. It's talking to the mothership. You can talk to it to see data with a dashboard. You supply power, and you supply an antenna. These are like $30. It's not like $1,500 or whatever I see 9,700 will cost. Antennas, you don't need much. This is an image I snagged off a UK amateur site. This is a 435 meg quarter wave ground plane, And you can see, looks like he mounted a chassis connector here and bent up a little piece of aluminum, put in 4 radios, and then has the vertical element. And these work, even though it's that simple, and we'll see even something simpler here in a little bit. This will pick up these little satellites. I've built in a EggNOGS antenna. This is from Halibut Electronics, Mark Smith, a ham. He's one of the hosts on the Ham Radio Workbench, if you listen to that, that podcast. And this is something he developed for the SatNOGS network, similar to TinyGS, and based on the egg beater design. And somebody on the Ham Radio Workbench podcast one night says, "Oh, you ought to call it the EggNOG antenna." So that's where the name comes from. It's a kit for $79, so they can spend a little more money. And what you have here is a kit of everything that's in this white cap. So you supply the wires. It's just number 12 gauge solid house wire will work. And this is a circular polarized antenna. And traditionally how you build these is that your coax has to feed both loops. Although one loop you have to have a longer piece of coax that's a quarter wave longer at the operating frequency, taking the velocity factor into account. So electrons don't go down coax at the speed of light. They propagate through at about 66% of the speed of light. So that affects the length of a quarter wave section. Mark's design here removes you having to monkey around with coax sections to do the phasing. So this is one of the 2 boards that's in that end cap. This is a balun. For your HF antennas, you may have taken coax and looped it through several times, have it up by the antenna. Well, this is what works for the 450 meg band. The quarter wave phasing section is within the artwork in this board. So the balun is just a loop of coax through there. You solder the shields on one side, you flip it over, and the center conductor goes through a hole for each one of these, and it solders to a pad on the other side. And then you solder on this connector. And Mark mentions very well in his instructions, it's very detailed, which I didn't totally pay attention to. So I built all this, and I had some troubles. We'll get to that in a second. So the board with the balun on it mounts to the round board here, and that fits in this PVC end cap, which comes with a kit. And Mark actually drills the 4 holes with a CNC machine, so everything fits together. And when you mount the delay board on here, or the main board to the, call it the connector board, if you insert the board where it says RHCP for right-hand circular polarization, those 2 arrows line up, you're in right hand. You turn the board 180 degrees, and you can see it says left hand over here. It'll then say left hand. So we want to set this up for right hand circular polarization. Then you measure out some wire and bend it up. You just, with the nuts on here, fasten it down. It mounts on a 2-inch PVC pole. And here it is, just bungee cord to the side of my deck. Everything can fit inside here, so now you have a waterproof enclosure. So here it is before I put it all in the tube. Here's the antenna and its board with a little short coax with SMA connectors to the receiver controller board, powered by a USB wall wart here, connected to an AC extension cord. Push it all down the pipe, and you're up and running. Let me just back up here to here. So I put all this together, put it out there, and then I wait. And I'm not receiving anything. You go, what is going on? And I thought, okay, something's wrong. and I took my antenna analyzer out there and hooked it up, and the SWR was like at 15-to-1 across every frequency. So, okay, I did something wrong inside here. So I brought it back in onto the workbench, took it apart, and where the center conductors go through the hole, let me just, where the center conductor goes through the hole on the board, marks this to make sure the insulation is sticking out past the other side. Otherwise, the center conductor may short up against the edge of the printed circuit board, which is what happened. So I just loosened up the solder joint, pushed it so the insulation of the center poking through the hole, and put it all back together, and it was working. I put a second station together, so here's another board running, and here I'm using the rabbit ear antennas that come with the RTL SDR dongle kits. And that bag of stuff you get is this little antenna, SMA connector, so I'll put it in there. I'm powering it with a battery bank, and sitting in the window, it works surprisingly well. I've since then taken that receiver board and stuck it in this ammo case. This was my first TinyGS receiver I built several years ago. And I put this together, put the board in there, and put a battery in there, and set it outside, and you start receiving satellites. You connect to the board using Wi-Fi. And that's how you can see the dashboard and see the performance and the operation of the system. This is the dashboard you connect to using Wi-Fi, and this is kind of the main thing I like to watch. And what we have here, first of all, is a little map, and this little dot here is the location of, so here's the little dot here, shows the location of the satellite, and the one that we're listening to, its latitude and longitude, what its azimuth and elevation. This is what I find amazing. I don't understand what's going on here. Why am I hearing a satellite that's 3 degrees below the horizon? Because here's the telemetry, here's the data. It'll spit out 100 bytes. Here it is here, all in ASCII or just a big long string. Here it's been formatted as a hex dump. Here it is formatted as ASCII over here. Shows you your signal strength, signal to noise, and that I'm connected to the TinyGS MQTT server, so my data is going out to the network, and that I am online and ready to run. So this is a interesting page to watch. So to improve things, I bought a couple preamps. So this is what I bought. This is a wide band, 20 to 4,000 megahertz, 20 megahertz to 4 gig for $30. This will amplify just about everything. In fact, probably too much. We'll get to that in a minute. Here's another one I bought, and this is a two-way signal booster, which can be used for Meshtastic. So when you're receiving, it acts as a preamp, and when you're transmitting, it acts as a power amp. And since it's for the 433 meg band, this most likely has some filtering in there. I just received this in the mail yesterday, and it's pouring down rain today, so I haven't been able to go out and put this online to see how it works. So, and one of the things we learned last night, where is it here? With Rob, is that the board is only labeled with inputs and outputs. It's in the silk screen if it doesn't focus over here. And the comment was, it's input and output relative to what? Receiving or transmitting? So Rob put it, excuse me, in line with his antenna and receiver board, stuck it outside, and got nothing for about 10 or 15 minutes. And somebody in the chat room mentioned, Rob, why don't you go out there and turn it around, hook it up the other direction, and then it started working. You will notice now that since we learned which end is for the antenna and which end's for the radio, I've marked it on there, so I won't make the same mistake. And you can power this. You just solder this onto the 5-volt and ground pads on the little board there. $30. So, if you look at your station on the TinyGS website, you will see a bunch of stats of your online and how many packets you've received since going active, and how long it's been since the last packet, and so on. But you also see this bar graph here at the bottom. Where's my mouse? And this shows you how many packets you're receiving per day. And these are all the different satellites that I've received. So here it is. For these 3 days, I was running the rabbit ear antennas inside, sitting on the windowsill, facing west with no preamp. I'm getting, between 280, 300 or so packets a day. I took that little wideband preamp, put it in line with the antenna, and I almost doubled the amount of packets per day. Cool. Okay, so that's an improvement. I had it probably offline on these 2 days. And this was a partial day. The days start at 000 UTC. So if you make a change, you want to do that around that time, so you get a whole 24 hours in your bar graph here. I then moved the radio over to the quarter wave ground plane box, mounted on the railing about 4 feet to the west of the window where the rabbit ear antenna was. And the first day, you can see I received almost 100 more packets per day compared to the rabbit ears, and still less than the preamp. So the next thing I want to try and do is put the wide bandwidth preamp in the box here and see if we can get this up higher here. So these are some of the things you can play and experiment around with the TinyGS station. You let it run for a while and you think, well, let me change the antenna, maybe put a preamp in, maybe move the antenna, move it away from the house, away from the trees, and try different things. And you can see the results, and just let it run for a day or two and see what happens. So if you go on the TinyGS, the K7AGE3 station is now the quarter wave ground plane box. This is K7AGE2. This is the EggNOGS antenna. And you can see this performs a lot better. I'm getting between 600 and 700 packets a day. But what happened here? This is where I put that wideband preamp in line. And I was getting like nothing. There's like 40 packets here. And it was driving me nuts. I'd go out there, and yet I had power. I bring the guts back inside, measured the voltage on it. It was like at 4.2 volts. I wondered if that wasn't high enough. I got instead of powering it from the little ESP32 board, I powered it through the onboard USB connector, put it all back out there, jam it in the pipe. I'm getting nothing. I took my TinySA spectrum line analyzer out there, hooked it on the output of the preamp. I saw all this stuff. In fact, I did that sitting here at the workbench. And I would see those same signals without the preamp, but with the preamp, they were about 20 dB, more or less higher. So my thinking is maybe I was overloading the front end of the little ESP32 board with that antenna, but not with the rabbit ear antennas. Maybe not quite as sensitive or wide frequency. I don't know. But took the preamp back out. Took the preamp back out and brought my reception to more packets per day. This is where spam risk. Put them in voicemail. So I want to put that, so the next thing I'm going to try here to do is put that bidirectional this thing here in that pipe and see how that works. Probably tomorrow when the rain stops. This is Saturday, November 1st. I'm making this recording. Since I ran into this problem, I found this 433 bandpass filter on Walmart of all places. I found it on Amazon too, but hopefully the delivery on Walmart is supposed to be a little bit faster. So for 10 bucks you get a filter. I bought two. When I ordered all these ESP32 boards the other day, I bought three. So, you know, if you blow one up or damage it or something, it's, as Gordon West says, you need to have backups for your spares. So three's the number. So if you go onto the TinyGS page for your station and scroll down, it'll show all the satellites in each packet that you received. And I've been in email communications with Josh at Cornell University. He's part of the project. In fact, he's working on his PhD dissertation. I believe it has to do with this whole project. And one of the questions he asked me is, how well does your station receive the lower power satellites? Some of these satellites run at 1 watt, 3 watts, and 9 watts. So he wanted to see how the lower power satellites were being received by my station. So I scrolled through the long list of received packets. Here's this Pico 1B-8 satellite. It runs at 631 milliwatts. This CSTP runs at 800 milliwatts. So here it is, 1,600 kilometers away. What's that, like 1,000 miles? Basically 9 degrees elevation. The received signal strength is a minus 128 dB. Signal to noise ratio at -7. Here it is like 3 minutes later. It's further away. It's lower elevation. Received signal strength is lower and 5 dB worse signal to noise ratio. The CSTP, 800 milliwatts, it was essentially 900 kilometers away, 30 degrees elevation, similar RSSI signal strength, minus 129 dB, signal to noise ratio of -6 and -7. So on my quarter wave box station, had the Pico satellite, and let's look at this timestamp, 14/22/41. I go back to this satellite, same timestamp, so it received the same packet on both stations. Here it's -128, -7. Over here it's -128 and -9. So that little quarter wave antenna is working almost as good signal-wise as the EggNOGS, although I don't receive as many packets. So I'm just amazed at how well this simple stuff works. Here's the CSTP at low elevation, under 3 degrees, -126, signal to noise of -8.5 and 7.5. So this is some of the data that you can see of how your ground station is working. So why do we need to monkey around with the TinyGS satellites when we're going to aim for the Alpha Cubesat solar sail mission? Well, when the solar sail is released, it only operates at like 100 milliwatts, so it's going to be really weak. And it's only going to last for about 2 days before it gets pulled back into the Earth's atmosphere due to the drag. So if you built your station and did all the configuration exactly for the Cubesat, it's Chipsats, which are the little transmitters on the sail. You only have 2 days and you may not have your station optimized. So you set it up and do all your optimization using the TinyGS satellites, and when we know when the sail is going to be deployed, then go into the TinyGS configuration and you change the configuration for it to only receive that one satellite or that one class. It may be multiple transmitters that are on the sail, and don't clutter up or be missed out on an opportunity to receive the sail because other satellites are overhead. So the Alpha Cubesat, this is a Cornell University project, and it's basically they got a ride up to the space station. It's in a Cubesat launcher on the outside, and here's the Cubesat, and this sail gets all folded up and fits in there until they can release it out. So there's been other solar sail missions. This is the Alpha. This shows the relative size of the different sails. And this is one from the Planetary Society. And I really don't know much about or anything about these other two. So this shows you how small this system or this sail is going to be. So what happens is the sun strikes it, and the energy from the sun accelerates and pushes the sail. So this sail has to fit inside the Cubesat. So they fold this thing all up in an origami technique. Pretty neat. If you go to the Cornell Alpha website, you can find it easily. Just Google Cornell Alpha Cubesat mission, and I'll put links in the excuse me, notes below. There's this video that they have, and it's worth watching. They go through the engineering of the whole package, what the goals are, what the sail material is made out of. It's a different material. When the energy or the light hits the sail, it's a reflective material that bounces it straight back and doesn't scatter it as it comes back, which makes it more efficient for the propulsion part. And how it all folds up in there, what the release mechanism is, which is common on a lot of the satellites. They have basically a low ohm resistor or something that's going to create heat when they run current through it, and touching that is like a nylon cord, and the nylon cord is holding a spring compressed, so when they send the current through the resistor, it warms up, melts the nylon or whatever, and then the spring releases and it'll push it out. And probably is not a very strong spring. It just give it a gentle nudge out the hatch of the sail. Opens up and gets pushed out. Another view of the sail, and this is where the Chipsats. These are the electronics and the transmitter and everything that's going to ride on the sail. And this is what the Chipsat board is. It's got a lot of stuff on here. Here's the dipole antenna for the 437.4 megahertz. It's going to transmit on. This is the dipole antenna for the GPS receiver. Here we have an LED for the lock. Nobody's going to be able to see that. Some mounting holes. This is the GPS or the GNSS receiver. Got a solar regulator here. Don't know where the solar panel is. Maybe it's on the other side here. Here's the radio transceiver, 437.4 LoRa, 100 milliwatts. Here's the LSM9DS1. I think this is a one of these MEMS units. It's got maybe like the the position sensor knows what the attitude of the board is, which way it's pointing, because they have magnetorquers in the Cubesat, so they can get the satellite orientated in the required direction to release the sail out. It's just not going to be random coming out. Here's the microcontroller, the crystal for that, and a temperature sensor. And I think there's maybe 2, maybe 4 of these that are on the sail. Again, you got to have spares for your backups. And here's a shot from their webpage showing some of the team. You can get an idea now of what the size of the sail is, kind of what the material is. You can see where all the fold marks are. Here's the Cubesat itself. All the frame on this has all been 3D printed. This has been a multi-year project at the university. You know, some of the students have started working on it, and have since graduated and they're out working now, and other students are, you know, recently working on this project. So it's kind of neat to see so many students get involved, and you know, really a lot of smart kids working on this stuff. It's really kind of neat. Another kind of graphic of the sail. You can see where the chipsats are. It says 4 of them, maybe 1 on each side. I'm not totally sure. This was an experiment. They put a prototype or experimental version on a high altitude balloon with looks like probably 4 GoPro cameras, and had the spring mechanism, and they can release this out. I believe this is in the video, so you can actually see it. On the real mission, the real Cubesat does have a camera on there, so they can get images of the sail as it goes out and capture it opening up. We won't be able to receive that, but I'm sure we'll see pictures that they receive. We'll talk about that in a second here. So again, you know, it is on the space station. It wasn't clear from their webpage and stuff because this has been written over many years. So the Cubesat is on the space station in a launcher and waiting to be deployed. So the Cubesat itself is not using LoRa or any ham frequencies. It's using a Adrenium modem and radio to go up to their satellites for control and the telemetry. So that's how the university people can see the telemetry and control the satellite with it in its orbit anywhere in over the Earth. So the Iridium system allows for that. But once the sail is released, that's the LoRa part, and that's the part that we can receive. So like I just mentioned, the Cubesat is on the ISS, it's on the space station, and just yesterday afternoon I received a update through their email list, and it's now been delayed for the deployment about 2 weeks to the 1st of November. So that gives us a couple more weeks to get ready to try and receive this. You can send a message to Andy. Like I said, Josh is working on his PhD, so if you send an email to Andy at this email address, so 43dprinting@gmail, that's pretty easy to remember, 43dprinting, and ask Andy to add you to the Alpha Mission mailing list. If you're on LinkedIn, you can find this as well, and there's a little more updated information here than there is on their website. They have an excellent, they call it the Chipsat Sail Ground Station Guide. It's about 25 pages long. It goes through what the mission is. It goes through all the pieces that you need to acquire or buy. You know, the board, they have a quarter wave ground plane antenna that they've used, you know, the different cables and adapters and, you know, all this stuff that you may need, a case to put it in if you want to build everything and buy everything from scratch. They go through how to assemble it. They go through how to configure it and how to do the special configuration when it's for when it's deployed. And something in the newsletter yesterday mentioned is that look at the online guide. I'd say often, because any changes to the mission and stuff, they'll put it in the guide. You know, they may change what the actual name of the satellite is, so it'll be documented in the guide. So you'll need to look at that, especially at that time just before the sail is deployed, to make sure you have the latest information there. And I'll provide a link below for that guide. This is the link here. There's no way you're going to be able to type all that in. This is the QR code for it. So if you can just grab your camera right now or pause the video, boom, you can go to the website and get the station guide. It is a doc. It is a .doc guide. I think almost anybody can open up a Word document, either in Word or Libre Word or text or write or whatever they call it, you know, in that software suite. So that's all I have here. Just let me think here for a moment if there's anything else I wanted to cover. Let's see here. Trying to think of any other things that were in Josh's update, but the main thing is the deployment date's been delayed to December 1st. Some of these items, when you go to order it, may be a couple weeks to get, so if you're thinking about this, you want to get involved with it. Again, you need the 433 meg version of these boards, not the 915 meg version of the boards that we use for Meshtastic. There are some 915 meg satellites, but I've never tried to configure a board to receive anything there. So make sure you buy 433 megahertz components, the boards, preamps, amplifiers, whatever. Otherwise, it's not going to work for you. And I think this will be a neat project. I'm looking forward to see if we can actually receive a 100 milliwatt satellite from orbit. We won't really know what the orbital parameters are, but it should be similar to the space station. I don't think it's going to be too dramatically different, so that'll give you some indication if you track the space station when you might be able to receive a packet. Again, they expect it to only stay above the atmosphere for 2 days, so we won't have a lot of time to adjust and change things. So optimize your station using the TinyGS series of satellites and their network. And I'll just mention here in closing, the other fun thing I like to do is receive the slow scan from the ISS station. There's some rumors about a event during November, during this month. So stay tuned. I'll do an update. Follow me on Twitter at K7AGE. I keep posting updates, what I'm doing, anything I receive from the Aries group about the ISS, SSTV, and anything from TinyGS. I think that's it. This is Randy, K7AGE. I hope you get on. $30, loads of fun. Build an antenna. We hams can do that. Thanks for watching. Give me a thumbs up, please, and a like and a subscribe, and share this on to your buddies. Thank you.